Hello, my name is Ramiro Gálvez from Universidad de Buenos Aires, and I'm going to present this paper entitled A Unifying Framework for Modeling Acoustic Prosodic Entrainment, Definition and Evaluation on Two Large Corpora. My co-authors are Lara Gauder from Universidad de Buenos Aires, Jordi Luque from Telefónica Research, and Agustín Gravano from Universidad de Buenos Aires. Acoustic prosodic entrainment is the tendency of interlocutors to become similar to each other in the way they speak. Research on the effects of acoustic prosodic entrainment is still preliminary, in part because the way acoustic prosodic entrainment in conversations is modeled is far from standardized, and different papers usually use different techniques. Moreover, most of the reported findings rely on small corpora, generally collected under experimental setups. In this paper, we propose a unifying approach for modeling acoustic prosodic entrainment in conversations. The proposed methodology is simple and flexible enough as to generalize acoustic prosodic entrainment metrics used in previous studies. Moreover, we evaluate the proposed framework on two large and very different corpora of spontaneous telephone interactions. Concretely, we test if three entrainment metrics derived from the proposed framework allow to predict positive social aspects of conversations. Okay, let's dive into the methodology. What we got here is, for a given dialogue and a given feature, in this case f0 min, the evolution of that feature for each speaker in the dialogue. Black represents speaker A, gray represents speaker B. Each segment in the figure represents an interpausal unit or IPU, and the height of that segment represents the value of the feature in that IPU. The strategy that we are going to follow is to fit a function to estimate the evolution of the feature for each speaker in the conversation. This is something that previous methods already do, for example TAMA, but unlike TAMA, what we are going to do is to fit a continuous function. As the plot shows, what we do is to fit nearest neighbor regressions to each speaker IPUs. This provides some advantages. First of all, the functions will be defined for the whole dialogue for each speaker. Moreover, the predictions or the functions will have high granularity in portions with many IPUs. This is kind of like TAMA, but with adapting window length. With these functions, we can calculate entrainment metrics very easily. For example, we can calculate proximity, how close are the features on average during the dialogue with these expressions. This is an example of a high proximity dialogue, and this is an example of a low proximity dialogue. We can also calculate how the features converge during the conversation, and we can use this expression to calculate convergence. This is a high convergence example, this is a low convergence or divergence example. Moreover, we can also calculate synchrony, which is calculated using these expressions. And what it shows is how the features co-evolve during the conversation. This is an example of a high synchrony dialogue, and this is an example of a low or anti-synchrony dialogue. These three metrics have already been used in previous papers. What we are showing here is that we can adapt them to take continuous functions as input. Up to now, I have presented the methodology we proposed in this paper. From now on, I will present results from an empirical study where we test if metrics derived from this methodology predict positive social outcomes. As I told before, we ran a series of machine learning experiments where we tested if metrics derived from the proposed methodology have any predictive power over positive social aspects of conversations. We studied two corpora, which differ in their spoken language, domain, and positive social outcome attached. First, we studied the switchword corpus in American English. The switchword corpus consists of nearly 2,400 recordings of spontaneous telephone conversations. The outcome that we tried to predict was naturalness. Basically, each transcriber, after transcribing each dialogue, had to rate each dialogue in terms of its naturalness. So that is the score we are trying to predict. The other corpus that we are going to work with is the call center corpus in Latin American Spanish. It consists of nearly 20,000 inbound call center conversations, and the outcome to predict in this case is self-reported customer satisfaction. For each dialogue in each corpus, we calculated proximity, convergence, and synchrony metrics on F0 max, F0 min, intensity max, intensity min, noise to harmonic ratio, jitter, shimmer, and speech rate. Overall, we calculated 24 features. We also consider external features, such as speaker gender, conversation length, among others. Concretely, what we did is that we trained and evaluated XGBoost models using different sets of input features. For example, we trained one model using only synchrony metrics, another model using only proximity metrics, another model using only external feature metrics, and so on. For each of these models, we use as the evaluation metric area under the curve. We use tenfold cross-validation to estimate our out-of-sample performance, and we search for hyperparameters using random search strategy. Then, for the best model we found, for each input set of inputs, we use SHAP values to interpret what they do with these features. These tables present our results. The left table presents results for the switchboard corpus. We see in the top panel that when we do not include external features, the best model is the one that includes only synchrony metrics, and it obtains a result equal to 0.575. Remember that a chance result would be an area under the curve equal to 0.5. So this is above chance. When we include external feature, only considering external features achieves a better result than the best model that does not include them, right? 0.627. But what is really interesting is that when we add the synchrony metrics to this model, we achieve an even higher result. Well, when we see the results for the call center corpus, we see that when we do not include external features, the best model is the one that includes the 24 entrainment metrics, and the result obtained is equal to 0.582. When we only include external features, we obtain a result equal to 0.537, not higher than the one that does not include them. And when we add to the external features all the acoustic prosodic entrainment metrics, our results are equal to 0.582, equal to not including external features. So it seems that in this case, the external features that we considered are not that really predictive. These tables present our feature importance estimates. As you can see, for the switchboard corpus, the most important feature is that both speakers were female, then speech rate synchrony, then the length of the conversation, and so on. You can see that the top of the ranking consists mainly of external features, but the second most important is a synchrony related one. For the call center corpus, the top two features are speech rate proximity and speech rate synchrony. Then we can see that conversation length is the third one. Seeing feature importance estimates is really interesting, but we would rather like to see how the model effectively uses these features. In this slide, we present partial dependence plot for those features detected as important in the previous analysis. What this plot shows is that for each feature, how its value relates to the model's prediction. Take this case for example. Here is a dummy variable which takes the value 1 if both speakers are female and 0 otherwise. And it shows that if both speakers are female, the predictions tend to go up relative to when they are not. And in this case, it shows the relation with speech rate synchrony. It shows that high values or really low values of speech rate synchrony tend to lower the model's predictions. The top 10 panels are the partial dependence plot for the switchboard corpus, and the bottom 10 are for the call center corpus. What we can see here is that it's not the case that always a higher value of entrainment is associated to a higher value of the predicted outcome. We can see also negative relations and inverted U patterns, where really high value or really low values are associated to low predictions. Moreover, we can see that the same features, take for example this case and this case, does not necessarily share the same pattern across corpus. We can see that in this case we observe an inverted U pattern, and in this case we only see negative values for positive values of the entrainment metric. Summing up, in this paper we propose a unifying framework for modeling different types of acoustic prosodic entrainment in natural conversations. Moreover, using this framework, we tested on two very different corpora whether three entrainment metrics provide valuable information for predicting social outcomes. Results suggest that these metrics effectively relate to positive social outcomes. What we find is that AUC scores validate the proposed approach and suggest that acoustic prosodic entrainment is related to positive social outcomes. We also find that the features which predict positive social outcomes depend on the outcomes being predicted and the corpus itself. Finally, dependence plots suggest that the way in which predictive models make use of entrainment metrics is quite complex. So, I hope you enjoyed the paper, and I am available for any type of comment or questions or whatever you feel like. Thank you very much.